Hello, in this video we'll be reviewing Unit 6, which covers basic integration techniques. For number 1, we want to integrate 3 plus 2x minus 4 over x squared with respect to x. So we start by finding the antiderivative of 3, and then we'll do so for each term. The antiderivative of 3 with respect to x is 3x. The antiderivative for 2x, we're going to use our power rule where we add 1 to the exponent and then divide by the new exponent. So the 2 is a constant multiple, that stays there, so it's 2x squared divided by 2, which simplifies to just x squared. And then for the next one, if you've memorized that the derivative of 1 over x is negative 1 over x squared, that's really similar to what we're trying to integrate here. The only difference is ours is multiplied by 4. So this is going to be plus 4 over x. Now, if you don't recognize that, or you haven't memorized that the derivative of 1 over x is negative 1 over x squared, then what I would recommend would be to rewrite this as 4x to the power negative 2, and then apply your power rule for integration. Okay, this is an indefinite integral, so at the end, we always need a constant term, plus c. Number 2, again, we'll just integrate term by term. So the derivative of what is sine x? Well, the derivative of cosine x is negative sine x, so the derivative of negative cosine x is sine x. So we need negative 2 cosine x. And then the derivative of sine x is cosine x, so we want minus sine x plus c. So I'm just thinking in my mind, the derivative of what is going to produce what I'm seeing inside of my integral. Okay, number 3. Now, we don't have a product rule for integration, so we want to simplify this as much as possible before we try and integrate it. And I'm going to do that by distributing the 4x to each of these terms in the parentheses. So I have 4x times the square root of x. So I'm not integrating yet, I'm just simplifying. So 4x times the square root of x plus 4x over x squared. I'll go ahead and write that out now, and then we'll simplify it some more. Let's continue to simplify this. So 4x root x is the same as 4 times x to the power 3 over 2. That's x to the power 1 times x to the power 1/2. Plus, and then x over x squared is 1 over x, so this becomes 4 over x dx. Now, if you'd like, you can factor out a 4. And when we factor out a 4, we can bring it all the way outside of our integral. So then I'm just integrating x to the power 3/2 plus 1 over x dx. So the antiderivative of x to the 3/2 is x to the 5/2 divided by 5/2, which is the same as multiplying by 2/5, plus, and then think the derivative of what is 1 over x. This is our one special case where we can't use the power rule because it would force us to divide by 0. So the derivative of ln x is 1 over x, but when we integrate, we need absolute value around our x to make sure we protect the domain. And then plus c. Now, the plus c can be inside of the brackets here or outside of the brackets. It doesn't matter because c is just a placeholder for the constant term that's going to come at the end. So whether we write plus c and then distribute the 4, or whether we just close our brackets and then put our plus c, both ways will be correct. So now I can distribute the 4 in here, and I get 8 over 5 x to the 5/2 plus 4 ln absolute value of x plus c. Now, if we had the plus c inside of our brackets and we distributed the 4, you can write plus 4c. That's completely fine. But 4 times c is still just a constant. So it's okay to still just call that plus c. For the next set of problems, we're told that f of x is an even function And the integral of f from 0 to 4 is 9 pi. We're also told that g is an odd function, and the integral of g from 0 to 4 is 12. So for number 4, we want to find the integral of f from negative 4 to 4, and we know that f is an even function. So if f is an even function, then integrating from negative 4 to 4 will give the same result as if we integrate from 0 to 4 and multiply our answer by 2. Even functions are symmetric about the y-axis. So we can split that integral in half and just find the right half of it and multiply it by 2, and we'll get the same result. And we know the integral of f from 0 to 4 is 9 pi, so now we have 2 times 9 pi, which is 18 pi. Number 5, we want the integral of g from negative 4 to 4. Now g is an odd function, and with an odd function, if we integrate from negative 4 to 4, we're just going to get 0. Half the area is going to be above the x-axis, half the area is going to be below the x-axis, and they're going to cancel each other out. Number 6, we want the integral of g minus f from negative 4 to 4. So we can separate this into two integrals. So we have the integral from negative 4 to 4, g of x times dx, minus the integral from negative 4 to 4, f of x dx. And we know the integral of g from negative 4 to 4 is 0, minus, and the integral of f from negative 4 to 4 is 18 pi. 0 minus 18 pi, or just negative 18 pi. Number 7, we want to integrate 3f plus 1 on the integral from 0 to 4. So let's use some of our properties of integrals to simplify this a little bit first. So we can separate this into two integrals, the integral of 3 times f of x from 0 to 4, and the 3 times f of x. That 3 is a constant multiple, so we can bring it outside of our integral. So it'll look like 3 times the integral from 0 to 4 of f of x times dx, plus, and then the integral from 0 to 4 of 1 dx. And usually you wouldn't see the 1 written there. It would just say the integral of dx, which looks kind of funny. But it just means 1 times dx, so we'll be finding the antiderivative of 1 there. Okay, but let's go back to our first term. We know that the integral of f from 0 to 4 is 9 pi. So we have 3 times 9 pi plus, now we're not told what the integral of 1 is from 0 to 4, but we can find that ourselves. The antiderivative of 1 with respect to x is just x, and then we evaluate that from 0 to 4. And here's where we sub in our top value, minus, and then sub in our bottom value. So we get 27 pi plus, when I sub in the top value, I get 4, minus, when I sub in the bottom value, I get 0. So I end up with just 27 pi plus 4. Number 8, we're going to separate this into two integrals. And the first one will be the integral of f from 4 to 0. Now we don't know the integral of f from 4 to 0, but we know the integral of f from 0 to 4, which is just the opposite of the integral from 4 to 0. So I'm going to go ahead and flip the bounds. Instead of going from 4 to 0, I'm going to go from 0 to 4. And when I do that, I have to multiply the integral by negative 1. And I'll do the same thing for the g of x. I'm going to flip the bounds and make it go from 0 to 4, and when I do that, I have to multiply by negative 1 in front. So now I have negative, and we are given the integral of f from 0 to 4, that's 9 pi. So negative 9 pi minus, and then the integral of g from 0 to 4 is 12. So I get negative 9 pi minus 12. And number 9, again, I'm going to flip the bounds here. So I'm going to make it the integral from 0 to 4. And when I do that, I have to multiply by negative 1. And then I'm going to separate this into two integrals. So f of x times dx minus, and then here when I flip the bounds, to multiply by -1, so that double negative makes this a plus in front of this integral, g of x dx. So now I have negative, the integral of f from 0 to 4 is 9 pi, plus the integral of g from 0 to 4, which is just 12. So negative 9 pi plus 12. Number 10, evaluate the definite integral. So we want to integrate 3 cosine x minus sine x times dx from 0 to pi over 4. So we'll start by finding the antiderivative of 3 cosine x. The derivative of sine x is cosine x. So this is 3 sine x minus, and then the derivative of cosine will give me negative sine x. So I want to add a cosine x here. And I do a quick mental check by taking the derivative of this answer to make sure it's a match. The derivative of 3 sine x is 3 cosine x. The derivative of plus cosine x is minus sine x, so that works. And I'm evaluating this from 0 to pi over 4. So I sub in my top value, so 3 times the sine of pi over 4. The sine of pi over 4 is 1 over root 2, or if you prefer, root 2 over 2. Plus, and then cosine pi over 4 is also 1 over root 2. So I have that minus, and now I need to sub in 0. 3 times the sine of 0. The sine of 0 is 0, so that's just 0, plus the cosine of 0, which is just 1. And now let's simplify. I've got 3 over root 2 plus 1 over root 2, which is 4 over root 2 minus 1. And if we want to rationalize this, you don't have to. If we want to rationalize this, we can multiply by root 2 over root 2, and then we get 4 root 2 over 2 minus 1, which is 2 root 2 minus 1. Number 11, we're going to integrate 2 minus sine x times dx from 0 to pi over 6. So the integral of 2 is 2x, and then plus cosine x. Again, I'm doing a quick mental check. The derivative of 2x is 2. The derivative of cosine is negative sine x. So that works, and we evaluate from 0 to pi over 6. So here when we sub in pi over 6, we get 2 times pi over 6, which is pi over 3, plus the cosine of pi over 6 is square root of 3 over 2, minus, and now we sub in 0. 2 times 0 is 0, plus the cosine of 0 is 1. So I have pi over 3 plus square root of 3 over 2 minus 1. And there's no easy way to simplify that, so we'll just leave it like so. Number 12, we want to integrate 3 root x over 2x on the interval from 1 to 9. So there's no quotient rule for integration. We're going to have to simplify this before we proceed. The 3 over 2 is being multiplied by root x over x, and that constant multiple can come out. So I'll bring the 3 over 2 outside of my integral. And now I'm just integrating square root of x over x dx, and we can simplify that. Square root of x over x is the same as 1 over square root of x. And now I see that I would like to put the 2 back in. I brought it outside the integral, but I'd rather have it inside the integral because I know the derivative of square root of x is 1 over 2 root x. So this is just one of my derivatives I have memorized. So when I see this in an integral, I immediately know the antiderivative of this is the square root of x. So I have 3 and then square root of x evaluated from 1 to 9. So we sub in the top value. Let me write my 3 here first. I'm going to sub in the top value. So I have square root of 9, which is 3, minus, and then sub in the bottom value. Square root of 1 is 1. 3 times 2 is 6. Use the table below to evaluate the definite integrals. Number 13. We want the integral of f prime from -2 to 0. So the antiderivative of f prime of x is f of x. This is going to equal f of x evaluated from -2 to 0. So it's going to be f of 0 minus f of -2, and we can read those values from the table. F of 0 is 11, minus f of -2 is -5, and that gives us 16. Number 14, the integral of f double prime is f prime, and we're evaluating at the upper bound minus, and then evaluate at the lower bound. So f prime of 1 is 1, minus f prime of -2 is 4. 1 minus 4, -3. Number 15. The integral of f double prime of x is f prime. So we have f prime evaluated at 2 minus f prime evaluated at 0. That's just this part of it right here. So then I move on to the next term. Now I've got minus 2/3 times, and then when I integrate f prime, I just get f, and I evaluate at the upper bound minus, and then evaluate at the lower bound. So f prime of 2 is 0, minus f prime of 0 is -9, minus 2/3 times f of 2 is 12, minus f of 0 is 11. So that gives me 9 minus 2/3 times 1, or just 9 minus 2/3. So that would be 27 minus 2/3, or 25/3. Number 16, snow is accumulating at a rate of r of t inches per hour. Give units for each of the following. So keep in mind that regular r of t is already a rate. It's inches per hour. So in part A, when we find r prime of t, we're taking the derivative with respect to time. We're going to have another per hour at the end of our answer. So if r is already inches per hour, then r prime is going to be inches per hour squared. Part B, we're finding the antiderivative of r. So the r of t is already inches per hour, and then we're multiplying it by dt, which is hours. When you multiply your inches per hour by hours, you just get inches. So the integral of r of t is just going to be inches. Part C, we're integrating r of t from A to B, but that's still just going to be the antiderivative of r, which would just be inches, evaluated at time B, minus the inches evaluated at time A. So this is also just going to be inches. Whether it's an indefinite integral or a definite integral, we're undoing the derivative here. So we're undoing that rate, and we get the amount of change, so just inches. Now part B, this part of our answer right here, we saw in part C, is just inches. But then we're multiplying that by 1 over b minus a. So essentially, we're dividing it by b minus a. And b minus a is the change in time. So we're dividing this integral by time, and the units for time are hours. So this one is going to be inches per hour. 17. A particle moves along the x-axis with velocity v of t equals 1 plus 2t minus 0.25 t cubed. Find the average velocity of the particle on the interval from 1 to 3. Average velocity is the change in position over the change in time. So we can either do the average velocity formula as p of 3 minus p of 1 over 3 minus 1, but we don't have the position equation. So we probably want to think of this instead as the average value of the velocity equation. So I'm going to use the average value formula. I want the average value of the velocity. And for that, I'm going to use the average value formula, which is 1 over b minus a, in this case 3 minus 1, times the integral from a to b of the function you want the average value of, so v of t dt. This is going to give me the average value of the velocity, or just the average velocity. Now, hopefully you can see a connection between these two formulas, because when we integrate, well, first of all, the 1 over 3 minus 1, multiplying by 1 over 3 minus 1 is the same as dividing by 3 minus 1. So that's the connection to the denominator here and here. And then the integral of v is just p, and it's a definite integral. So we evaluate p at 3 minus, and then we evaluate it at 1. So this part of our average value formula corresponds to this part of our average velocity formula. So we can approach this problem using either one of these formulas, but since we have the velocity equation, I think this second method will be easier. So 1 over 3 minus 1, 3 minus 1 is 2, so now I can just say 1/2 times the integral from 1 to 3 of v of t dt. Now we can integrate v of t by hand just using our power rule. It wouldn't be too bad, but let's go ahead and use our calculator to integrate this. So I'm just going to keep calling it v of t for the time being, and let me pull up my calculator. Okay, so I can enter this all in one go. 1/2 is the same as 0.5. 0.5 times the integral, so math 9, from 1 to 3, and then I'm going to enter my velocity equation, 1 plus 2t minus 0.25 t to the power 3. And we're integrating with respect to t, and of course our calculator is calling our variable x, but that's fine. And we get an answer of 2.5. So this whole thing is equal to 2.5. That's going to give me my average velocity on the interval from 1 to 3, or the average value of the velocity on the interval from 1 to 3. Part B, find the average acceleration of the particle on the interval from 1 to 3. So again, we have two different formulas we can use to find average acceleration. Our first one is to remember that average acceleration is the change in velocity over the change in position. So we can say average acceleration is v of 3 minus v of 1 over 3 minus 1. Or we can use the average value formula, in which case we would be taking the average value of the acceleration, and that would be 1 over b minus a, so 1 over 3 minus 1, times the integral from a to b, so from 1 to 3, of the thing we want to find the average value of, so a of t dt. These are just two equivalent formulas. They're both going to give us average acceleration, so you can use whichever one you like. However, for this problem, if we use the formula on the right, we have to have the acceleration equation, which we do not. It's not difficult to find the acceleration equation. We would just take the derivative of our velocity equation. But since we already have our velocity equation, it's probably going to be easier to use the formula on the left. So in my calculator, I'm going to go ahead and enter my velocity equation in y1. That's the 1 plus 2t minus 0.25 t cubed. So my velocity equation is in y1. And now I want to find the velocity at 3 minus the velocity at 1 over 3 minus 1. So I'm going to do this in one go in my calculator. I'm going to call up y1, because that's my velocity equation. So velocity at 3 minus velocity at 1 over 3 minus 1. And I get negative 1.25. Negative 1.25. And we don't have units in this problem, so I don't have to worry about that. Average velocity on this interval, negative 1.25. Part C, if the initial position of the particle is x equals negative 3, find the position at time 4. Again, there are two different ways we can approach this problem. We can try and find the position equation by integrating v of t and solving for c. We know that at time 0, the position is -3, so we could use that to solve for c. That is one way that we could do this. The other way we can do this, and since this is a calculator active problem, the second way I think is going to be a little easier, is we can set up an integral involving the time we know the position and the time when we want the position. So we know the position at time 0. We want the position at time 4. We're going to set up an integral to go from 0 to 4. This will give us the change in position from 0 to 4. We already know where it was at time 0. So the integral will give us how much it changed. We can add that together and then get our final position. So we're going to integrate velocity to determine the change in position. And that's going to give us the position at 4 minus the position at 0. Okay, so I still have my velocity equation entered in y1. So on my calculator, I'm going to use math 9 to integrate from 0 to 4. And that gives me 4. So I know that 4 is equal to p of 4 minus p of 0. And I know p of 0. P of 0 is -3. So 4 equals p of 4 plus 3. I can subtract 3 on both sides and I get 1 equals p of 4. So the position when t is 4 is just 1. Another way of thinking about that, the integral gives us the change in position. So at time 0, the position was -3. That's where it was at time 0. And then we integrated from 0 to 4, and we got 4. So if you add the change in position to the initial position, you get the final position. That would give us the 1. Part D, find the total distance traveled from time t equals 0 to t equals 5. Total distance traveled. So if we set up an integral from 0 to 5, and we integrate velocity on that interval, we get the net distance traveled. We just get the change in position or the displacement. If we want total distance, then we have to integrate the absolute value of the velocity. On our calculator, we can do this easily. Math 9, we're integrating from 0 to 5, and then you enter absolute value. So math over to num for number, and then 1 absolute value. And then we enter our velocity. My velocity is still in y1, so I'm going to call up y1. And I'm getting 22.950. Again, we don't have units, but this is my total distance traveled. If we integrate velocity and we don't use absolute value, then we're going to get the net distance traveled. Part E, find all times on the interval from 0 to 5 when the speed of the particle is increasing. So I prefer to figure this out by looking at the graph of the velocity equation. That's not the only way we can do this, but it's the way that I prefer to do it. I have the velocity equation in y1, so I'm going to look at the graph. We were told to work on the interval from 0 to 5, so I'm going to set up my window to go from 0 to 5, and then I'll adjust my y values if I need to. Let's just make sure we know what's happening on the right side of the graph here. So I will make my y min lower. Let's try -20. Okay, so here is the graph of my velocity. The speed is increasing whenever velocity is positive and increasing or negative and decreasing. So it looks like there are a couple places where that happens. Let me resketch over here. We've got something about like that. I may have exaggerated a little bit. The velocity, this is the velocity equation. So my velocity is positive when it's above the x-axis. So I'm looking for positive and increasing, and that happens until this relative max right here. So velocity is positive, 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 and increasing. Here it's still positive, 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 but it's decreasing. Here it's negative, 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 and decreasing. So this part of the graph here, it represents speeding up. And then this part of the graph here also represents speeding up. When velocity is positive and increasing or negative and decreasing, then our particle is speeding up. So I need to find this value by relative max, and I need to find this x-intercept. Okay, so this maximum is occurring at 1.633. And then my x-intercept, .051. Okay, so find all times on this interval when the speed of the particle is increasing. That would be from, and let me just do trace 0, enter to see. Okay, at 0 the velocity is 1, so it's increasing from 0 with 0 included up to 1.633. Speed is increasing on the interval from 0 to 1.633. So I just checked at 0, the velocity is positive 1. So we'll include that in our interval. But at 1.633, that's where we're right where we're changing from speeding up to slowing down. So I'm not going to include that point. And then also from 3.051 to the end of our interval, which is 5, and at 5, let's check, we can do 5, enter. At 5, the velocity is negative 20.25, so I can include 5 as a point where the speed is still increasing. Okay, so now the reason is different for each of these, so I probably should have done this separately. Yes, let's do this separately. So speed is increasing on the interval from 0 to 1.633 since v of t is positive and increasing. So when v is increasing, that tells us the acceleration is positive. And then speed is decreasing. No, that's not what I wanted to say. Speed is also increasing on the interval from 3.051 to 5, since v of t is negative and decreasing. When v is decreasing, that means the acceleration is negative. Number 18, the table shows the velocity of a vehicle recorded at various times over a 2-hour interval. Estimate the acceleration of the vehicle at t equals 1 hour. So our table shows us various times and then the velocity at those times. If we want to estimate acceleration, acceleration is the derivative of velocity, or the average rate of change of our velocity. So we're going to pick the closest two surrounding points. We know the velocity at 1. We want the acceleration at 1. We know the velocity at 1. We're going to pick the closest two surrounding points and calculate the average rate of change on that interval. So we'll do 80 minus 88 over 1.25 minus 0.75, which is negative 16. So a of t, I'm not going to write a of t equals negative 16 because we don't know that for sure. This is just our estimate. So we're going to say is approximately equal to negative 16. And we can figure out our units here, so let's do that. If velocity is kilometers per hour, then acceleration will be kilometers per hour squared. Part B, if possible, find the average acceleration of the vehicle on the time interval 0 to 2. If not, explain why we can't determine that. The average acceleration is the change in velocity over the change in time. Average acceleration would be v of 2 minus v of 0 over 2 minus 0. So v of 2 we can read from the table. V of 2 is 50. V of 0 is 0. And then over 2 minus 0. 50 over 2 is 25. Average acceleration is going to have the same units as acceleration, so kilometers per hour squared. Or we can say in our setup here, the numerator, change in velocity, that was already kilometers per hour. And then in our denominator, this was the change in time, which was hours. So we have kilometers per hour over hours gives us kilometers per hour squared. Part C, if possible, find the average velocity of the vehicle on the time interval from 0 to 2. If not, explain why we can't determine that. So average velocity would be the change in position, so p of 2 minus p of 0, over the change in time. We don't have any information about p in our table, so we can't find it using this formula. Now there is another formula for average velocity. We can use the average value formula, and for that we would do 1 over 2 minus 0 times the integral from 0 to 2 of our velocity equation. And although we have velocity values in our table, we don't have the velocity equation, so we can't use this formula either. So in this case, the average velocity cannot be determined from the information that we have, since we don't have what we'd ideally like to have is the position function. Although if we had the velocity function, we could integrate to find the position function. Since we don't have the position function, this cannot be determined. Okay, part D, if possible, find the total distance traveled by the car during the 2-hour time interval. If not, explain why the value cannot be determined. So for total distance on this interval, we would want to integrate from 0 to 2, absolute value of our velocity. Now we can see in our table, I guess we're making some assumptions here, but it appears as though the velocity is always positive except at time 0. So I'm not really concerned about a change in direction, but even if we are able to drop our absolute value and say, oh, we just need the integral of v, or p of 2 minus p of 0, we don't have that information. We don't have the velocity function, so we can't get the integral. So let's say since we don't have the velocity function, this cannot be determined. Now, for both of these parts, we concluded that we can't find this value, but let me point out, we can approximate this value using a Riemann sum. So this would be a good time to use a Riemann sum. This is a scenario where we might want to do that. A Riemann sum is going to approximate the area under the velocity function, which is going to be the change in position. That's what we're trying to figure out here. So if we want to integrate velocity from 0 to 2, we can approximate that value using a Riemann sum. Part E, interpret the meaning of the integral of vt dt from 0 to 2 in the context of the problem, including units. If we integrate velocity, we'll get p of 2 minus p of 0, which is the change in position. Remember, if you integrate a rate of change, you get the amount of change. So velocity is the rate of change of position. So when we integrate, we get the amount of change in the position, or in other words, net distance. So 0 to 2, v of t dt gives the net distance traveled from t equals 0 to t equals 2 hours. And I didn't work the units in there. So the net distance traveled, the units there would be kilometers. So let me just insert that here, in kilometers, from time t equals 0 to t equals 2 hours. Okay, then part F, interpret the meaning of 1/2 times that integral in the context of the problem. Well, this is the same as 1 over 2 minus 0 times the integral from 0 to 2. When you see that, think average value. This is the average value formula for velocity. This is going to give us the average velocity on this time interval. So this represents the average velocity of the vehicle on the interval (0 to 2). I guess we can include those endpoints in our times. And again, I didn't work those units in there. So the average velocity is going to have the same units as velocity, kilometers per hour. So it represents the average velocity in kilometers per hour of the vehicle on the time interval from 0 to 2 hours. Part G, approximate, oh, here we go. We are going to use a Riemann sum. Approximate the integral of velocity from 0 to 2 using a midpoint Riemann sum with 4 subintervals of equal length. So we can't find the exact value of the integral of v from 0 to 2, but we can approximate it using a Riemann sum. 4 subintervals of equal length. So I'm going to go 0 to 0.5, 0.5 to 1, 1 to 1.5, and then 1.5 to 2. That takes me from 0 to 2 using 4 rectangles. We want a midpoint Riemann sum. So we're using midpoints as the height of the rectangle. The width of the rectangle, this first one is 0.5. Looks like they're all 0.5. 0.5, 0.5, 0.5. So to show my work, show my setup, I'm going to do 0.5 times 45 plus 0.5 times 88 plus 0.5 times 80 plus 0.5 times 58. Now, if you had noticed that they were all going to be multiplied by 0.5, you could alternatively have just said 0.5 times, essentially factoring out the 0.5, 45 plus 88 plus 80 plus 58. It makes for fewer button presses when we have to calculate that. So let me pull up my calculator and we'll compute that. 0.5 times 45 plus 88 plus 80 plus 58. 135.5. I integrated velocity. Velocity was kilometers per hour, so my answer is just going to be kilometers. And again, that's going to approximate the net distance traveled on that interval. And then part H, Now we want to approximate that same integral using a right-hand Riemann sum with 4 subintervals of equal length. So 4 subintervals again, I don't have to redo that, but let me erase my midpoints. This time we're doing a left Riemann sum. Nope, we are not. We are doing a right Riemann sum. So my heights are going to be 72, 95, 62, and 50. And I'll take the shortcut of factoring out that 0.5 since my intervals all have the same width. So now it's 0.5 times 72 plus 95 plus 62 plus 50 equals 139.5. And again, that'll be kilometers. 19. Find the average value of the function f of x equals x squared minus sine x on the interval from 0 to pi. We're going to use our average value formula. Average value formula. You have to memorize this one. Average value of f of x. We do 1 over b minus a, so pi minus 0, times the integral from a to b of the function you want to find the average value of, so f of x dx. And we can do this one by hand. That doesn't look like a difficult integral. So 1 over pi minus 0 is 1 over pi. And we're integrating from 0 to pi the function x squared minus sine x times dx. So 1 over pi. The antiderivative of x squared is x cubed over 3 minus the derivative of cosine is negative sine. So I want plus cosine x right here. And we're evaluating from 0 to pi. So we sub in the top value. Let me put my constant multiple out here. We're subbing in our top value. So I get pi cubed over 3 plus the cosine of pi. We'll simplify that in a moment. Minus, and then we sub in our lower limit, 0 over 3 plus the cosine of 0. Okay, so 1 over pi times pi cubed over 3. The cosine of pi is negative 1. And then we need to distribute our negative here. 0 over 3 is 0, so minus 0. The cosine of 0 is 1, and so then minus 1. So 1 over pi times pi cubed over 3 minus 2, and if we distribute the 1 over pi, we get pi squared over 3 minus 2 over pi. That's the average value of our function on the interval from 0 to pi. Number 20, the graph of f prime of x is shown below, and it consists of 2 semicircles and a line segment. Find the exact value for f of 3 minus f of 0. This is the graph of f prime of x. So f of 3 minus f of 0. We're looking at the derivative graph, but we want information about the antiderivative. So it looks like we're going to set up an integral. If we integrate f prime of x from 0 to 3, that's going to give us f of 3 minus f of 0, which is what they're asking us to find. Find f of 3 minus f of 0. So we can alternatively just find this integral instead, since it's equal to f of 3 minus f of 0. And this integral is the area under f prime from 0 to 3. We have the graph of f prime. So let's find the area from 0 to 3. So we want this area from 0 to 3, which is a quarter of this large circle. The circle here has a radius of 3. So the entire circle has an area of 9 pi, but we only want 1/4 of the circle. So it'll be 9 pi over 4. In part B, we're asked to find the exact value of f of 5 minus f of negative 3. let's erase this. F of 5 minus f of negative 3. That means I want to set up an integral that has the 5 on the top and the negative 3 on the bottom. So we're going to go from negative 3 to 5 of f prime. That's going to give us f, the antiderivative, at 5 minus f at negative 3, which is what we want. So we need the area from negative 3 to 5. From negative 3 to 3, that's just half of that circle. And remember, the whole circle had an area of 9 pi. We want half of that. So 9 pi over 2 plus, we have to go all the way to 5 now. The area from 3 to 5 is half of this little circle, and it's below the x-axis, so it has negative area. And this little circle here has a radius of 1, so the entire circle has an area of pi. We want half of that, pi over 2, and it's negative. 9 pi over 2 minus pi over 2 is 8 pi over 2, which is 4 pi. So part B will be 4 pi. Part C, if f of 6 equals 3 pi over 4, find the exact value of f of 4. Let's set up an integral that goes from 4 to 6. Because we know that is going to be equal to f of 6 minus f of 4. And we know the value of f of 6. So we'll be able to solve for f of 4 as long as we can find the value of the left-hand side. And the left-hand side here is just the area between 4 and 6. So the area between 4 and 6, well, between 4 and 5, that's 1/4 of this little circle, and it's negative. The whole circle is pi. 1/4 of the circle is pi over 4, and it's negative. And then, so let me shade so that we're clear about what we just found there. And then from 5 to 6, we'd be finding this area right here, which is half of a 1 by 1 rectangle. So it just has area 1/2, but since it's below the x-axis, it's negative. And that's equal to f of 6, which we know is 3 pi over 4, minus f of 4. Now we solve for f of 4. So let me move f of 4 over to the other side. We get f of 4 equals 3 pi over 4 plus pi over 4 plus 1/2. So 3 pi over 4 and pi over 4 is 4 pi over 4, or pi plus 1/2. Pi plus 1/2. And part D. If the integral of f prime from 0 to 10 equals 20, find the integral from 7 to 10 of f prime. Well, we can find the area up to 7, but then we don't have the rest of the graph after 7. So let's go ahead and find the area up to 7. And when I say up to 7, I mean we're going to start at 0, not at negative 3, because ultimately we want to find the integral from from 0 to 10. So the integral from 0 to 10 is the same as the integral from 0 to 7 plus the integral from 7 to 10. Right? That's if we start at 0, stop at 7, and then pick right back up again at 7 and go to 10, that's going to give us the same result as if we went straight from 0 to 10. We know the integral from 0 to 10 is 20, so the right-hand side now is 20. We don't know the integral from 7 to 10. That's what we want to find. But we can figure out the integral from 0 to 7 using area. So from 0 to 7, we want this positive area minus this area, and then we're going to minus this area as well. So from 0 to 3, that would be our 9 pi over 4. From 3 to 5, that's minus pi over 2. And then from 5 to 7. 5 to 7, that's half of a 2 by 2 rectangle. Half of 4 is 2, so minus 2. Okay, 9 pi over 4 minus pi over 2. Pi over 2 is the same as 2 pi over 4. So that would be 7 pi over 4 minus 2. Okay, so 7 pi over 4 minus 2 plus this unknown value equals 20. So this unknown value equals 20 plus 2 minus 7 pi over 4. Not pretty, but there it is. Number 21, we're finding the derivative of the integral of the fifth root of t squared minus 1 dt from 1 to x. Using our shortcut here, we know our derivative will cancel out our integral, and then we have to evaluate this at x and at 1 and use our chain rule. So we substitute in the x and we get the fifth root of x squared minus 1 times the derivative of x, which is just 1. And then the constant term on the bottom, when we multiply by the derivative of the constant, we're going to get 0, so we can ignore that. And that is our answer. Number 22, our derivative will cancel out our integral. When we sub in the 0 and then multiply by the derivative of 0, we just get 0. Minus, and then we sub in our lower limit of integration, and we get 3x squared minus 1, and then we multiply by the derivative of that lower limit, which is 2x. And so we get, see if we distribute here and here and distribute the negative 1, we get 6x cubed negative, and we get negative 2x negative, so negative 6x cubed plus 2x. 23, our derivative will cancel out our integral, and we are subbing in sine x for t. So we get cosine square root of sine x times the derivative of sine x. Derivative of sine x is cosine x. Minus, now pi, our lower limit of integration is pi. That is a constant. And when we multiply by the derivative of pi, that's just going to be 0. So we can ignore that part. And this will be our final answer. Now you can't simplify this because it's not cosine times the square root of, it's cosine of the square root of sine x times the cosine of x. No way to simplify that. 24. We are given the graph of f of t. This is the graph of f of t, regular f. And we're given an equation for g of x. G of x equals the integral of f dt from negative 2 to 2x. For part A, we want to find g of negative 1. So g of negative 1, we're looking at g of x, and we're just subbing in negative 1. So that's going to be the integral from negative 2. And when I sub negative 1 in for x, my upper limit of integration is also negative 2. The integral of f from negative 2 to 2 is just 0. Just 0. Part B, find the value of g prime of negative 1. So for that, let's figure out what is g prime of x. I'm going to write that down here. G prime of x is the derivative with respect to x of the integral from negative 2 to 2x of f of t dt. And that is just f of 2x times 2. So if we want g prime of negative 1, we sub in negative 1 for x. We get f of 2 times negative 1, and then times 2. F of negative 2, we read from the graph. F of negative 2 times 2 is 4. Part C, find g of 2. G of 2, coming back to my equation for g of x, and I'm subbing in 2. So that's going to be the integral from negative 2 to 2 times 2, so from negative 2 to 4. f of t dt. That's the area under f. We have the graph of f, so now we're going to find the area from negative 2 to 4. From negative 2 to 4. From negative 2 to 0, I'm finding this area, which is a quarter of a circle with radius 2. A circle with radius 2 has area 4 pi. I need a quarter of that. So just pi. This part here is just pi. This part here is half of a 2 by 2 rectangle, so that's negative 2. And then this part right here is half of a 1 by 2 rectangle, so negative 1. And then this area right here is half of a 1 by 2 rectangle, so positive 1. So the integral from negative 2 to 4 is just the sum of those net areas. So pi minus 2 minus 1 plus 1 is pi minus 2. Now g prime of 2, I'm going to my g prime equation. G prime of 2 is f of 2 times 2 times 2. So f of 4 times 2. F of 4 times 2. F of 4 we read off the graph. F of 4 right here is 2. So 2 times 2, that gives me 4. Part E, find g double prime of 2. So now we need an equation for g double prime. Let's do that over here. G double prime of x is the derivative of g prime of x. So now I want the derivative of f of 2x times 2. The times 2 I'm going to move to the front like that. So I want that derivative of that. 2 times, my derivative is still going to be 2 times. The derivative of f of 2x, that's f of stuff, use the chain rule. It's f prime of 2x times the derivative of 2x times 2. Or we can multiply the outside 2's together and get 4f prime of 2x. So if I want g double prime of 2, now it's going to be 4 times f prime of 2 times 2. So 4f prime of 4. I have the graph of f. F prime of 4 is going to be the slope at 4. The slope at 4. Well, that's problematic. If we look at our graph, at 4, the slope does not exist because 4 is clearly marked as an end point. We have a slope leading up to 4, but at 4, the derivative does not exist. F prime of 4 does not exist. So I'm just going to say does not exist. We can't calculate g double prime of 2. Part F, find g prime of negative 1/2. So let's look at our g prime equation. That's f of 2x times 2. So g prime of negative 1/2 will be f of 2 times negative 1/2 and then times 2. F of negative 1 I can read from the graph. Oh, maybe not. F of negative 1, let's make sure I did that right. G prime of negative 1/2 is f of 2 times negative 1/2. Yep, that's f of negative 1 times 2. So the problem is that f of negative 1 is this point right here, and that's not a whole number. I can guess what it is. I mean, I can approximate to the best of my ability. It looks like it's about 1.7. I'll go with 1.7. 1.7 times 2. Give me 3.4-ish. And then part G, find the value of g double prime at negative 1/2. So let's go to our g double prime equation. That's going to be 4 times f prime of 2x. So 4 times f prime of 2 times negative 1/2. Hopefully we'll have better luck with f prime at negative 1. Nope, not really. F prime at negative 1 would be the slope of the curve at negative 1. So I'm just imagining my tangent line there. I don't know what the slope at that point is exactly. We can sort of like estimate it. I'm having a hard time drawing a straight line on my screen here. Well, if I went with 1.7 here, that means for my slope, I'm going it looks like I'm going down 0.7 and over 1. So negative 0.7 is what I'm guessing my slope is in this case, negative 0.7. So 4 times negative 0.7 would give me negative 2.8. And our last set of problems deal with U-substitution. So here we want to integrate tan 4x over cosine squared 4x with respect to x. Now, it's helpful to try and separate the problem into two parts or more, where one part is the derivative of another part. So I'm noticing that, or I'm kind of thinking in my head, okay, what's the derivative of tangent? What's the derivative of cosine? To try and see what I want to choose for my u. And I know the derivative of tangent x is secant squared x, and I don't have secant squared x, but I have 1 over cosine squared 4x, which is the same as secant squared 4x. So I do kind of have the derivative of tangent in this problem. So we're going to let u equal tan 4x. Then we're going to take the derivative of that. The derivative of u with respect to x, so du dx equals, and to take the derivative of tan 4x, we need to use the chain rule. This is tangent of stuff. So the derivative of tan stuff is secant squared stuff times the derivative of the stuff, so times 4. Now the 4 we don't have in the original problem, so I'm going to divide both sides by 4, and I'm going to multiply both sides by dx, so that I get 1/4 du equals secant squared 4x. And instead of writing secant squared 4x, I'm going to write 1 over cosine squared 4x so that it looks like what we have in our problem. And then remember, I multiplied both sides by dx. So the 1 over cosine squared 4x dx, all of that right there, just turns into 1 over 4 du. Okay, so now my new integral is 1 over 4 du, and then the tan 4x just becomes u. So now I'm just integrating 1/4 u du, which gives me 1/4 u squared over 2 plus c. And then for our final answer, well, I can multiply the 4 and the 2, so I get 1 over 8, and then u squared is tan squared 4x plus c. Number 26, we're integrating 6x squared secant squared x cubed over tan x cubed dx. So again, kind of think through the possibilities. Is one part the derivative of another part? And this is we've got multiple things going on in this problem. So the derivative of x cubed is 3x squared. So that's going to help us get rid of that x squared in the front. And then the derivative of tangent is secant squared. So that's going to help us get rid of the tangent in the bottom. So it looks like this might be a double u sub. But let's see if we can get away with just showing the work for one. So I'm going to let u equal tangent of x cubed. And then I'm going to take the derivative, so du dx equals, the derivative of tan stuff is secant squared stuff times the derivative of the stuff, so times 3x squared. And a couple things we can do. I can divide both sides by 3 and get a match for secant squared x cubed times the x squared. I could multiply both sides by 2 and get a, let's do that. I like that idea. Well, first let's multiply both sides by dx, and then I'm going to multiply both sides by 2. So I'll have 2 du equals secant squared x cubed times, and I said I was going to multiply by 2, so the 2 times the 3 is going to give me a 6, x squared, and then I also multiplied by dx. Now I've got a perfect match right here. Secant squared x cubed times 6x squared dx. That's all of this. All of that is just equal to 2 du. So when I rewrite my integral, it's 2 du. That replaces all of that stuff that I circled. And then tan x cubed is u, so now it's just 1 over u du. And the integral of 1 over u is ln absolute value u plus c. So final answer, 2 ln absolute value tan of x cubed, close my absolute value, plus c. That was complicated. If you're up for it, remember, you can check your answer by taking the derivative. If we take the derivative of our answer, which would involve a double chain rule, we should get back to the integrand that we started with. Okay, 27. The inside function, if there's a square root in the problem or a cube root or a whatever root, usually what's inside of the root is our u, so let's try that. U equals 3x squared minus 12. And then I'll take my derivative, du dx equals 6x. And I'm trying to get a match with 4x dx. I've got du equals 6x dx. I can divide both sides by 6. So I have 1 over 6 du equals x dx. And if I really want to get that 4 to match, now I can multiply both sides by 4. 4 over 6 reduces to 2/3. Du equals 4x dx. So now my 4x dx, right here, 4x dx, can be replaced with 2/3 du. So my integral becomes 2/3 du times the cube root of u, since 3x squared minus 12 is equal to u. And that's 2/3 times the integral of u to the power 1/3 du. So integrating that using the power rule, we get 2/3 times u to the 4/3 times 3/4 plus c. And we can simplify that. Our 3's cancel, and 2 over 4 reduces to 1 over 2. So 1/2 u, which is 3x squared minus 12, to the power 4/3 plus c. We want to integrate x plus 3 over the square root 2x plus 1. So we'll let u equal 2x plus 1 since that's inside of a root. And we'll take the derivative. Du dx equals 2. And then I'll multiply by dx. Du equals 2 dx. I don't have a 2, an extra 2 in my integrand, so I'm going to divide both sides by 2. I get 1/2 du equals dx. And that's going to allow me to substitute for this dx. I don't have an x plus 3, so we'll still have to work with that. So I've got the integral x plus 3 over square root of u, and then the dx gets replaced with 1/2 du. So we still have to deal with the x plus 3. We got to get that x out of there. So I'm going to go back to my original substitution equation that relates u and x, and I'm going to solve that for x. I get u minus 1 equals 2x, so u minus 1 over 2 equals x. And now I can substitute that in for my x. So 1/2 integral. I need x plus 3. So u minus 1 over 2 plus 3, that's divided by the square root of u. So it's starting to get messy. So instead of dividing by the square root of u, I'm going to move that square root of u up to the numerator. When I do that, I have to give it a negative exponent. So I'm going to write it as u to the power negative 1/2. That was a really weird looking u. U to the power negative 1/2 du. And then we'll simplify from here. So 1/2 integral. I'm going to, okay, let's think, what's the best way to simplify this? I can just go ahead and distribute the u to the negative 1/2. Or I could split this up. No, I don't want to split this up. We'll just go for it. I'm just going to go ahead and distribute. So it's got to be distributed there and there and there. So I've got u times u to the negative 1/2 is u to the 1/2 over 2. And then negative 1 times u to the negative 1/2 is minus u to the negative 1/2 over 2. And then plus 3u to the negative 1/2. All of that du. I feel like I probably lost people there. So I'm wondering if I should have simplified that differently, if there was maybe an easier way. Let me try something else. This isn't wrong. I mean, we can keep going with this. But just from experience, I feel like that probably would have confused a lot of people. Instead of writing that as u to the negative 1/2, let me keep it dividing by the square root of u. But dividing by the square root of u is the same as multiplying by 1 over square root of u. Okay, I think I'm going to like this one a little bit better. So now when I distribute, it's going to be like that. Okay, 1/2 integral, and then I've got u minus 1 over 2 times 1 over the square root of u plus 3 times 1 over the square root of u, like that. Okay, we still have to go further with simplifying because we can't integrate while we still have products and quotients. So from here, I can multiply these first two fractions together. I get u minus 1 over 2 times the square root of u plus 3 over the square root of u du. Okay, now I need to split this up again. U over 2 root u minus 1 over 2 root u. And 1 over 2 root u, I'm not going to do anything with that. I like that just like that is because I know that's the derivative of the square root of u. Plus 3 over the square root of u. So 3 over the square root of u, I would really like a 2 in front of that square root on the bottom. So I'm going to multiply this fraction by 2 over 2. Oh, now they're all 2 over 2 root u. That's actually really nice. Okay, no, not the first one, because the first one has a u on the top, so that doesn't work. All right, let's keep going then. We got to simplify that first one. U divided by the square root of u is the square root of u. So we get square root of u over 2 minus 1 over 2 root u plus 6 over 2 root u du. Equals 1/2. Now let's go ahead and integrate. I'm running out of room. So square root of u is u to the 1/2. And the dividing by 2, that's a constant. So I can kind of ignore that. I just bring that out. Dividing by 2 is the same. I can just bring out the 1/2. And the integral for u to the 1/2 is u to the 3/2 times 2/3. And then 1/2 times 2/3 is just 1/2. So I'm going to go ahead and simplify that now to save space. Oh, what did I say that was? 1/2 times 2/3 is 1/3. Okay. So 1/3 u to the 3/2 minus the square root of u plus 6 square root u. And those are like terms. So we can add those together. Negative root u plus 6 root u is just 5 root u. Let's go ahead and do that. 5 root u. Plus c. And then we can distribute our 1/2. So we would get, I'm going to come over here to the left, we would get 1 over 6 u, now I have to put 2x plus 1 back in for u, to the power 3/2 plus the 1/2 times the 5, it's 5 over 2, and then square root of u, so square root 2x plus 1 plus c. Kudos if you got that one on your own. Number 29, we want to integrate 8e to the 1 minus 4x dx. So we'll let u equal our exponent, 1 minus 4x, and then take the derivative. Du dx equals negative 4, multiply by dx, so du equals negative 4 dx. And I don't have a negative 4 dx, I have an 8 dx, so I'm going to multiply both sides by negative 2. Negative 2 du equals 8 dx. And now 8 dx is going to be negative 2 du. So our integral becomes, the 8 dx gets replaced with negative 2 du. And e to the 1 minus 4x is just e to the u. So when we integrate that, we get negative 2 e to the u plus c equals negative 2 e to the 1 minus 4x plus c. Wow, that was a lot easier than the last one. Okay, home stretch. Number 30. We want to integrate 3 times the natural log of x plus 1 over 2x plus 2. Now we have to make a wise choice with our u. We've got some possibilities here. Do we want u to be ln x plus 1? Do we want u to be x plus 1? Do we want u to be 2x plus 2? If we go with the idea that u is our inside function, we might want to say u is x plus 1. But I think we're going to run into trouble if we do that. Let me just do it, because I think that's what most people would probably do. If you let u equal x plus 1, then we just get du equals dx. Oh, I think this will still work out. It's going to be a little bit strange, but I think it's going to work. So then our integral becomes 3 times the natural log of u over, now 2x plus 2 is the same as 2 times x plus 1, and x plus 1 is u, so we'd have 2u right there. And dx is the same as du for this problem. Not always, just for this problem. Dx equals du. And then now we've got a problem just in terms of u, so that's good. We can try and integrate. However, we have a quotient, and there is no quotient rule for integration, so we kind of get stuck again where, looks like we have to do another u substitution, and now we've already got u's in our problem, so we're going to have to call it something else, which is fine. In this case, let's just call it w, because we've already used x and we've already used u. So we'll go with w. I would let w equal ln u, because the derivative of that then, dw du, is going to be 1 over u. And we have there's a hidden 1 right here, right? 1. There's my 1 over u right there. And ln u becomes w. So now I have 3 over 2 times w times dw, if that makes sense. Like, you can multiply both sides here by du, so we get dw equals 1 over u du. 1 over u du right here, so all of that becomes dw. And then we get integral of 3 w dw over 2. And 3 over 2 can come out. And then we're just integrating w dw. So then it's 3 over 2 w squared over 2 plus c, which is 3 over 4 w squared. We have to do our reverse substitution here. So ln of u squared, but remember our original problem was not in terms of u, it was in terms of x. So then we have to do a reverse substitution again right here. So it's 3/4 times ln of x plus 1 squared plus c. Okay, so that does work. It gets us to the answer. I'm going to try this one other way because I think a better choice of u might be easier. Or not. We'll see. We'll see what happens. If we let u equal ln x plus 1, then I think we avoid the need for the double u substitution. So then we take the derivative of this. Du dx equals, we have to use chain rule to take this derivative. This is the natural log of stuff. So the derivative of ln stuff is 1 over stuff times the derivative of the stuff. Okay, so this is looking pretty good. I'm going to multiply both sides by dx to get u equals 1 over x plus 1 dx. Now in my problem, I don't have 1 over x plus 1 dx. I have 1 over 2x plus 2 dx. So look what happens if I multiply both sides by 1/2. Then I have 1/2 du equals 1 over, and I'm going to distribute the 2 down there, 2x plus 2 dx. So now 1 over 2x plus 2 dx, right here, 1 over 2x plus 2 dx, gets replaced with 1/2 du. So our integral becomes 1/2 du. 3 ln x plus 1 is just 3u, because in this case, u is ln x plus 1. And now we integrate. The 3 can come out. So 3/2 integral u du. We integrate. We get 3 over 2 u squared over 2 plus c, which is 3 over 4 u squared, and u is ln of x plus 1. We have to square that, plus c, and that is the same answer we got the other way. So it works whether you let u equal x plus 1 or u equal ln x plus 1. I think this way is a little bit easier because you don't have to do a double u substitution.